So this is our first lecture on chapter 2 on discrete logarithms and Diffie-Hellman. So this is the beginning of what is called public key cryptography. So we have two people, Alice and Bob, and they want to be able to send messages back and forth. But they don't want the message to be understood by anyone else. And there is a person, Eve, who is trying to discover what Alice and Bob are saying to each other. And we assume, this is always the case in cryptography, that every message Alice sends to Bob and every message Bob sends to Alice is intercepted and recorded. The message goes through, but it's intercepted and recorded by Eve. So Eve knows what they're sending to each other, but they're going to encrypt their messages so they're in codes. And hopefully, Eve isn't able to break the code even though she has the encoded message. Now, when you do your codes, many codes are based on a key. For example, in the Caesar cipher, you are translating every letter of the alphabet by a fixed number. That's the key. Like if A is going to be transmitted as B, and B is going to be transmitted by C, and so forth, you're shifting each letter by one, so the key is 1. And you can only use such a code if both Alice and Bob have a key. They have a way to recover the messages. So the first problem in cryptography might be, how do Alice and Bob have a key so they can encode and decode each other's messages? And so before they even have codes to begin with, they need to have a key. There might be a cryptographic algorithm, which everyone knows, Eve knows, but you can only encode or decode with the key. So when you're just setting out, how does Alice give a key to Bob, and how does Bob give a key to Alice, or how do they exchange keys so they can encrypt and decrypt, that is, encode and decode their messages? So that is, you might say, the first problem in serious cryptography, and it's solved by a method called Diffie-Hellman, based on two computer scientists, mathematicians, Diffie and Hellman, and as often is the case in mathematics and computer science, the name attached to something is not really the name of the people who first discovered it. This method was discovered by people actually working in the British spy service, the British, and was classified and then independently, Diffie and Hellman. It was also discovered independently by an undergraduate student at Stanford, but at the time that wasn't widely known. And Diffie and Hellman discovered it and published it, and it's called the Diffie-Hellman system. So the Diffie-Hellman system is a way for Alice and Bob to exchange codes in a way that Eve, who's intercepting every message, cannot figure out what the code is. And the code is based on something called the discrete logarithm. So that's what is the subject of section 2.2, discrete logarithms. So you fix a prime number P, and then we have the finite field with exactly P elements, Fp, which is the congruence classes Z mod Pz. So the representatives of the elements are just the non-negative integers from 0 up to P minus 1. And in section 1, we stated the theorem that for every prime P, there is a primitive root. So a primitive root in FP is an integer G, such that if you start taking the powers of G, of course, 1 is G to the 0, G squared, G cubed, and so forth, up to G to the P minus 2. So we have P minus 1 elements in this set. This is, in fact, everything in the field FP except 0. So this set is exactly the set of elements 1, 2, 3, up to P minus 1 mod P. So that's what a primitive root is. So for example, if you take P equals 7 and G equals 3, what are the powers of G mod 7? G to the 0 is 1 mod 7. G to the first power is 3 mod 7. G squared is 3 squared is 9, which is 2 mod 7. G cubed is 27, which is 6 mod 7. G to the fourth, well, G to the fourth is G squared squared, so that's 4 mod 7. And G to the fifth is 3 times 4 is 12, is 5 mod 7. So if you look at the congruence classes we got is taken by taking powers of 3, we have 1, 2, 3, 4, 5, 6. We have all the non-zero numbers, mod 7. So G is an example of a primitive root, mod 3. So let me just make a little table of that. So we have, let's say, H, and 3 to the H, mod 7, 0, 1, 2, 3, 4, 5. So 3 to the 0 is 1, 3. Let's see what the numbers were. 2, 6, 4, 5. So in this table, I have for each exponent H, 3 to the H mod 7. Now we could ask the following. Given every number, given any number, 1, 2, 3, 4, 5, 6. Let's call this A. What power of 3 gives you the number A mod 7? So 3 to the 0th power is 1. 3 squared is 2. 3 to the first power is 3. 3 to the fourth power is 4. 3 to the fifth power is 5. 3 to the sixth power, 3 cubed is 6. So this is the power to which you have to raise 3 to get the number A. And that's exactly what we mean by a logarithm. So this would be the logarithm of A, the base 3, mod 7. And so this is exponentiation. And this is taking a logarithm. This is what is called the discrete logarithm. And this is defined in general as follows. Given a prime P and a primitive root G, for every A, which is this means the non-zero elements of the field with 3 elements. So this is the numbers 1, 2, 3 up to p minus 1. The logarithm of A to the base G mod P equals H if G to the H is congruent to A mod P. So this is the discrete logarithm, which is extremely important in cryptography. And it has the properties, the usual properties of logarithm. For example, the logarithm of 1 is always 0. Because G to the 0 is congruent to 1 mod P. And the log of AB to base G is the log of A to base G plus the log of B to base G. So this is the addition formula for the logarithm. And it's an exercise in the homework to verify this identity. So that's what the discrete logarithm is. So it's very important. So it's basically just a definition, and then you do numerical exercises to get a good feeling for it. But you have a prime number P. For every P, there exists at least one primitive root. And once you have a primitive root G modulo a prime P, you can define the discrete logarithm with respect to the primitive root G. So for any number A, it's the power to which you have to raise G in order to get A. It's exactly the same as the definition of the logarithm that you're used to in high school math. So now we come back to our problem of you have Alice and you have Bob, and you want to exchange a key. You want to somehow, and you also have Eve listening in. So you need a method for Alice and Bob to have keys that will enable them to transmit messages securely.